Okay, thanks, Alan. So various people came up to me during the coffee break and said they were really tired and sleepy. I'm not sure if I should make this really animated to keep you all awake, or if I should do it very low key so you can just snooze away. But let's see what happens. To help you all sleep, I'm going to start off by explaining some stuff that you already probably know. A lot of the work on dichotomies has been on things related to homomorphisms. So I'm going to start off by talking about homomorphisms, firstly in a way that you'll completely recognize, and then in a slightly different way that will lead on to the more general partitions of graphs that I'm going to be considering. So we're used to thinking of a homomorphism from a graph G to a graph H being a function from the vertices of G to the vertices of H, such that any edge in G must get mapped to an edge in H. So, for example, if we look at this edge here, we see that one end gets mapped to here, the other end gets mapped to here, and we've mapped an edge to an edge. So that's the normal definition of homomorphisms. And notice that we don't care what happens to non-edges. So, for example, we can probably find a non-edge that's been mapped to an edge. Here we go, here's one. There's no edge between these two vertices, but they get mapped across to these two vertices, which are adjacent. So we don't really care what happens to non-edges. Okay, I'm going to look at homomorphisms in a slightly different way. I'm going to consider a homomorphism from a graph G to a graph H to be a partition of the vertex set of graph G. So each part of this partition is going to be labeled with a vertex of H. And I'm going to insist that if I've got a partition labeled with vertex U and a partition labeled with vertex V, if there's no edge between those vertices in H, I'm not going to be allowed to have any edges between any vertex in the part labeled with U and any vertex in the part labeled with V. Also, if I've got two vertices in the same partition, in the same part of the partition, I'm not going to allow any edge between those two vertices unless there's a self-loop on the corresponding vertex of H. So instead of looking at a map from vertices to vertices like this, I'm going to consider a partition. So I've partitioned into these blue sets here. Each of these parts of the partition, for example this one here, is associated with a single vertex over in H. I suppose I could have added an empty part here that's associated with the unused vertex of H. And you'll see, for example, that there are no edges within this part or within this part because neither of these two vertices have self-loops on them. And you'll notice that, for example, there is no edge between this part and this part. Actually, I should look at two. So here we have two vertices of H that aren't adjacent, and you'll see that there are no edges between the two parts labeled with those two vertices. Okay, so looking at homomorphisms as partitions of a graph. What do we know about homomorphisms? We've known for quite some time that there's a dichotomy for counting homomorphisms to a fixed graph H. So depending on the structure of your fixed graph H, either you can count the number of homomorphisms from your input graph to H in polynomial time, or it's number P complete to count those homomorphisms. When is it easy? When is it hard? Well, if every component of H is a clique with a self-loop on every vertex, then the problem becomes trivial. You can just map any vertex of G to any vertex of H, and all the edges that you could possibly need to be present are present, so you're allowed whatever edges you want in G. Alternatively, if H is a complete bipartite graph, how can we count homomorphisms from some graph G into a complete bipartite graph? Well, firstly, if G is not itself bipartite, then the answer is going to be 0. We can never have a homomorphism from an odd cycle into a bipartite graph, because a homomorphism to a bipartite graph induces a 2 coloring. Okay. On the other hand, because our target graph H is complete, excuse me, there's essentially no other restriction. Okay, we've got a bipartite graph G, we need to map it into H. Well, our choice is either to map the left part of G to the left part of H, and those vertices on the left can go anywhere we want on the left, or alternatively, we map the left part of G onto the right part of H. So we end up with 2 possible ways of doing it, times all the ways we can choose a vertex within the given side of H. So, and this then, actually we can power up to being not just H being a single component, but looking at all the components. And as long as every single component is of one of these 2 forms, you can have a mixture of the 2, a mixture of loopy cliques and unlooped bicliques. As long as those are the only components you have, counting homomorphisms to this graph is going to be easy, using these near-trivial algorithms that I've already described. Otherwise, it's number P complete. Okay, and another way we can look at homomorphisms is as constraint satisfaction problems. So constraint satisfaction problems, we have a bunch of variables. We want to assign values from some domain to these variables in a way that satisfies a given list of constraints. So to define a graph homomorphism problem as a constraint satisfaction problem, well, what are we trying to do? We're trying to map vertices of G to vertices of H. So the domain, the things that we map the variables to, is the vertex set of the graph H. And then our constraints are that every time we've got an edge in our graph G, that must be mapped to an edge in the graph H. So if R is the edge relation of H, we just slap a constraint on between any 2 adjacent vertices in G. Okay, so any homomorphism problem corresponds directly to a constraint satisfaction problem with a single binary relation. Okay, so I'm going to generalize from homomorphism problems to matrix partitions. And matrix partitions are defined by symmetric K by K matrices where every entry of your matrix is either a 0, a 1, or a star. And a partition of a graph, according to this matrix, is a partition of its vertex set into one set for each row, or if you like, column of the matrix. And we have the following properties. So if the ijth entry of the matrix is 0, we're not allowed to have any edges from the ith part of the partition into the jth part. Okay? Alternatively, so this corresponds exactly to the case with homomorphisms, okay, where there was no edge in the target graph of the homomorphism, we weren't allowed to have any edges between the partition corresponding to the endpoints of that edge. What we're adding is this middle point. If we've got a 1 in the matrix in position ij, that means that now it's obligatory to have edges. So in homomorphisms, it was never obligatory to have edges. It could be obligatory to have no edges, but now we've got forced edges. So if the ijth element of the matrix is a 1, then there must be every possible edge between vertices in part I and vertices in part j. And stars, as is commonly the case, just mean that we don't care. Okay, so if there's a star in the matrix, you can have any pattern of edges you like between the 2 parts of the partition. This is what happens if I and j are distinct. If I and j are the same, well, if we've got a 0 on the diagonal of the matrix, that just corresponds to the part being an independent set. So we're not allowed to have any edges within it. If we've got a 1 on the diagonal of the matrix, that corresponds to a clique. We don't force loops on each individual vertex, but we say that for every pair of distinct vertices in that part, there must be an edge between them. So if we've got a 1 in the matrix, the corresponding part of the partition must be a clique. And if we've got a star on the diagonal, which I haven't mentioned here, then again, we just don't care what the edge structure is within the ith part of the partition. Okay, and as I alluded to a moment ago, homomorphism problems are exactly these matrix partition problems where your matrix doesn't have any ones in it. Okay. So a couple of examples, which start with something familiar and then move on to things you might not have seen. So three colorings. What's a three coloring of a graph? Well, it's a division of the vertices of the graph into three parts, the colors. We're not allowed to have any edges between vertices of the same color. So that means that each diagonal entry of our matrix is going to be 0 to forbid edges within each color. But on the other hand, we don't care if there are edges or no edges between green vertices and blue vertices, for example. So every other entry of the matrix is a star. And of course, this is a homomorphism problem. It's just homomorphisms to a triangle. Okay, another example, a thing called a split graph. So a split graph is a graph where you can divide the vertex set, into a clique and an independent set, and nothing else. Okay? So any vertex that's placed in the first part must be part of a clique. Any vertex that's placed in the second part must be part of an independent set. And we don't care what edges run between this clique and the independent set, as long as we can split the graph into a clique and an independent set. And notice that this isn't a homomorphism problem. We've got zeros and ones in the matrix. Another example that isn't a homomorphism problem are things called clique cut sets. Clique cut sets do pretty much what you'd expect them to do. It's a clique that's also a cut set. Okay, so what have we got? We're dividing our graph into three parts. 1, 2, 3. The second part is going to be a clique. So we'll put a 1 on the diagonal there. The other two parts, well, they're just two parts of the graph. We're not requiring anything specific about those two parts of the graph. They can have edges or no edges or some combination of the two. However we please, so they both come out as stars. We also don't have any restriction on how each of the components outside the cut set is connected to the cut set. Okay, there could be some edges between them. There might not be any edges between them. But on the other hand, because it's a cut set, deleting it is supposed to cut the graph in two, so there better be no edges from part 1 across to part 3. Okay, so we'll say that this says there are no edges from part 1 to part 3, and this says there are no edges in the opposite direction. Okay.
Sorry. I don't want to divert you, but in principle you could add another value to the matrix to have a condition that there is at least one edge between the two. Or
Yes. And you could generalize it. I think people have considered the case where instead of saying that 0 means no edges at all, you could interpret 0 as meaning the graph is somehow sparse. And likewise 1 as meaning the graph is somehow dense for whatever definition of sparse and dense is making sense and working. That would mess up what I'm about to say now. So we'll go back to sparse meaning super sparse, no edges at all, and dense meaning every possible edge. Okay, so it turns out that we can also encode these matrix partition problems as constraint satisfaction problems. Our domain is just the indices of the matrix. So we're assigning to k different partitions, and our domain is going to be the identities of those partitions. We will have two binary relations, one of which corresponds to the places where you're allowed to have an edge, okay, either because you're forced to have an edge by a 1, or you're allowed to have an edge by a star. The other relation will correspond to the places where you're allowed to have no edge. Either you're forced to have no edge because there's a 0, or you're allowed to have no edge because there's a star. Okay, And we can code the partition problem for a fixed matrix M as a constraint satisfaction problem with this fixed constraint language. The variables, again, are just the vertices of the graph that we're trying to partition. And now we have two collections of constraints. For every edge in the graph, that edge had better go somewhere where we are allowed to have an edge. And for every non-edge of the graph, that non-edge had better fall somewhere where we're allowed to not have an edge. Okay, so we can express this quite happily as a constraint satisfaction problem. Now, we know how to solve constraint satisfaction problems. Okay, we know that for every constraint language, either you can solve instances of this in polynomial time, or you can solve, or trying to solve these instances is number p complete. And we have an algorithm in MP to decide which of these two is the case, given a specific constraint language. So if we can code matrix partition problems as constraint satisfaction problems, and we already understand the constraint satisfaction problem, I guess that's the end of the talk. Of course, there is a problem here. This refers to the complexity of deciding general instances of the constraint satisfaction problem. And if we look back here, the instances here have a very specific form. Okay? And the specific form that we have is that for every pair of vertices, or every pair of variables, there is either an R plus constraint between those variables, or there's an R minus constraint. In particular, there's not both, and we don't have any pair of variables with no constraints at all between them. Okay? So, actually, the these here refers to the opposite case. It's possible that for the constraint language that we've described, maybe there are instances, or a class of instances, where it's number p hard to count the satisfying assignments. On the other hand, maybe those instances don't look like the instances that we have. Okay, so it's perfectly possible that the instances that come out of M-partitions problems are of somehow intermediate complexity. Okay, if you allowed arbitrary instances, there'd be really hard ones, but because we've forbidden those instances, maybe we end up with something in the middle. Okay? So the CSP dichotomy doesn't actually resolve the complexity of matrix partitions, even though we can express matrix partitions as a CSP. Okay. So if we are going to, well, which we are going to try to resolve the complexity of this, we're actually going to look at a slightly different version of the problem where we add lists to all of the vertices. So you come across list versions of many problems, list colorings, list H colorings, or list homomorphism problems. What the list does is, instead of looking at, for example, general colorings, each vertex of your graph will come with a list of colors that you're allowed to apply to that particular vertex. Okay, so you might only be allowed to color a particular vertex green or red, for example, and not color that one blue. Okay, so now our instance of the problem is going to be a graph G. We've got a fixed matrix M. Our input will be a graph G and a list function lambda, which for each vertex of the graph tells you which part of the partition you're allowed to put that vertex in. Okay, and the question then is, how many M partitions are there of the graph that obey the restrictions given by the lists? Okay, so where every vertex is placed in a part that is in the list given to that vertex. And if we have a partition of that form, we say that it respects the lists. So most of the work that's been done on this problem has actually been on the list version. The advantage of the lists is that it allows us to perform reductions in many cases by forcing particular vertices of the graph to go into particular partitions, particular parts of the list partition, of the matrix partition. So, what's known? So this is the decision version of the problem. For any fixed matrix M, again, symmetric 0, 1 star matrix, the complexity of deciding if there exists at least one list matrix partition is quasi-polynomial or NP-complete, depending on the precise structure of the matrix. The formulation here is actually done in terms of a CSP that looks very much like this one. Okay. And what I'm going to talk about is counting these partitions. Okay, so now we find that although we couldn't deduce this from the CSP dichotomy, the result looks actually a lot like the CSP dichotomy in the sense that for any fixed matrix, counting the list partitions of some graph is either doable in polynomial time or it's number P complete. Pro tip when designing terminology, don't choose something with 9 syllables and then volunteer to give a talk where you're going to have to say it 150 times. But the dichotomy criterion is the existence of this thing called a derectangularizing sequence. First time. As I say, I will say derectangularizing sequence many times in this talk. Okay, so if you have one of these things, then it is hard to count the list matrix partitions. And if you have none of these things, then there is a polynomial time algorithm. In contrast to the case of counting homomorphisms, so firstly, the dichotomy criterion has a much fancier word. I mean, is rather more complicated to describe, not just because of the choice of terminology. And also, unlike the case for homomorphisms, actually the algorithm for counting the polynomial time cases is somewhat more involved. Okay, and also, we're not completely tied to lists. Some work has been done on the problem without lists for small matrices. So the decision version is known to be polynomial time or NP-complete. The criterion there is essentially if 3 coloring is hiding inside your matrix, then guess what? It's NP-complete. The interesting part is that if 3 coloring isn't hiding inside your matrix, then it turns out that there's a polynomial time algorithm. So that's for decision. For counting, there is again a dichotomy for matrices of size up to 4 by 4, which is not, I think actually this is 4 by 4 as well for the decision version, which isn't the biggest matrix you'll ever see. Actually, I think the techniques we used here could kind of be pushed to 5 by 5, but probably wouldn't be worth the effort. And the criterion actually here is exactly the same as it is in the list case. Hellherman and Navisi didn't prove it in those terms, but actually it does correspond to exactly the same thing as having one of these derectangularizing sequences 3 times. It turns out that one of these sequences in a 3 by 3 matrix can't actually be terribly complicated, which is how Hellherman and Navisi's criterion ends up being the same as ours. Okay, so how are we going to prove this dichotomy? So we prove it by, first of all, parameterizing the problem in terms of what lists you're allowed to use. Okay? So we'll define the problem number of L M-partitions, where L now is a set of allowable lists, is the same as the list M-partitions problem, but now as well as having lists that restrict what each vertex can do, well, somebody comes in and restricts what lists you're allowed to use as well. Okay, so you're given a set of lists, and you're only allowed to apply those lists to the vertices. On the other hand, of course, we can recover the general list partitions problem just by allowing any list as part of our so-called restriction. And from now on, I seem to have switched notation halfway through my talk, having previously referred to the parts of the thing as 1 up to k. Now I'm going to start calling that set D. Okay, so one of the properties that we'll need and use a lot is a thing called purity. So we will refer to a matrix as being pure if either it's a 0-star matrix or it's a 1-star matrix. Okay, so it's either a matrix with no 1s or a matrix with no 0s. These are matrices that we understand well. We understood before starting because they're homomorphism problems if they've got no 1s. And if they've got no 0s, it's essentially a homomorphism problem between the complement of the graph that you thought you were interested in. Okay, so pure matrix is essentially just a homomorphism problem. We'll say that our set of allowable lists is purifying if whenever you take two elements, so two of your allowed lists, and you restrict to the rows defined by one of those lists and the columns defined by the other, then you get a pure matrix. Okay? So, as an example, if we take the clique cut set matrix, and we only allow ourselves these two lists. So this list, if you apply it to a vertex, says this vertex must be in part 2, so it must be part of the clique. And this list says it must not be part of the clique. Okay? So if we applied these two lists, firstly, if we apply just the list 2, then we're cutting down to this 1-by-1 matrix in the middle, which is a pure matrix. It's got no 0s in it. Alternatively, if we look at rows 1 and 3 and column 2, then we get the matrix with the 2 red stars in it, which is also pure. It's got no 0s in it, for example. Or alternatively, we might restrict to the rows and columns given by 1 and 3, and then we get the matrix given by the red points around the edge, which again is pure. Okay, so this list is purifying, but on the other hand, if we said, for example, 1 and 2, 2 and 3, then we'd be restricting to this 4-by-4 matrix, 2-by-2 matrix in the corner, which is not pure. So, time to define the dread derectangularizing sequence. 4 times. I'm going to define for any subsets of the domain, and these subsets are naturally going to correspond to lists, but for now I'll define it for anything at all. So for any subset of the domain, subsets x and y of the domain, Rxy is just the relation that you get from the positions of the stars within the submatrix defined by x and y. Okay, so that gives us a binary relation on two subsets of the domain. I'm going to define a sequence of subsets of the domain again as being derectangularizing if, first of all, for every pair of these sets, when you restrict the rows and the columns using those pairs of sets, you always end up with a pure matrix. Okay, so this list of sets is purifying. And also when we compose all of these relations, so the relation that you get from the first two and from the second two and the third two and so on, take all of those relations, compose them together. If the result is not rectangular, then this sequence is derectangularizing. Okay, so you can see how we kind of railroaded ourselves into this bad name. What does rectangular mean? Rectangular just means that whenever we have these three components in our relation, so x1, y1, x1, y2, and also x2, y1, then we've got to have the fourth corner of the rectangle. Okay. So if we just go back here, this relation here, the 2 by 2, is rectangular because we don't have stars on three of the four corners. The relation defined by this 2 by 2 submatrix, on the other hand, is not rectangular because it has three of the four corners of the rectangle, but not the fourth. This 2 by 2 matrix, by the way, corresponds to counting cliques. Yeah, it's a partition or into a clique and anything you like, and you don't care what edges there are between the two. So this 2 by 2 matrix corresponds to counting cliques, and you'd expect that to be hard. Okay? Well, I expect you probably know that it's hard. Okay. So, moving towards proving the dichotomy, the first case we'll look at is where the lists that we're allowed to use are purifying. Okay, so the lists that we've been given break up the matrix into these pure submatrices that correspond to homomorphism problems. It turns out that if we are purifying, then the matrix partitions problem is in fact equivalent to a CSP. It's not just that you can translate to a CSP in one direction, it's that in a sense every instance of that CSP does correspond to a matrix partitions problem. So actually that will give us the dichotomy for the purifying case. We also require our set of allowed lists to be subset closed. Okay, so if a particular list is allowed, all of its subsets must also be allowed. The reason for that is that as we process the instance, we want to start restricting the list applied to any particular vertex, making it smaller and smaller, and we want all of those lists to be available to us. Okay. So this is the dichotomy that we get. Yeah. Okay, so this is the dichotomy that we get for the restricted list problem where the lists that we're allowed are purifying. So if we have a derectangularizing sequence, then it's number P complete. A derectangularizing sequence contained within the allowable lists, otherwise it's in polynomial time. So I'll go through a bit of the proof of that and then give some hints at how you'd prove the general case where your lists are not purifying. Okay, so this I've already mentioned. Implicitly, if you flip the zeros and ones in the matrix, this is equivalent to flipping edges and non-edges. Okay? So counting matrix partitions of a graph is exactly the same thing as counting the complementary matrix partitions of the complementary graph. Okay? And this is the thing that actually allows us to translate purifying instances into and back from constraint satisfaction problems. And So what the translation there does, do I have a slide about that? I do not. Okay. So if you look at the list applied to so we've got vertices V1 and V2 with lists L1 and L2. Now, because the lists that we're allowed to use are purifying, we know that the matrix between L1 and L2 is either a 0-star matrix, in which case it's a homomorphism problem, or it's a 1-star matrix, in which case it's kind of a complementary homomorphism problem. Well, according to which it is, we can either add the constraint of one kind or the other, and paste all of these things together across the boundaries to get... which one am I going? Sorry. So we translate from the list matrix partition problem to the CSP problem in exactly the way I told you earlier. The question is, how do we translate from a CSP back to a matrix partition problem? So you're given a CSP problem, and you need to produce a graph whose matrix partitions correspond to the solutions to the CSP. Okay, so if we have a relation between these that corresponds to a homomorphism problem, then we add the edge. If we have a relation corresponding to a complementary homomorphism problem, then we add no edge. And it turns out that when we paste all of those together, we end up with a graph that's perfectly well defined and whose number of M-partitions actually corresponds to the number of solutions to an arbitrary incoming CSP instance. Okay, going in the other direction, the definition of derectangularizing sequence will have looked familiar to those of you who are who know the counting CSP dichotomy, because the counting CSP dichotomy is all based around, can you define some kind of non-rectangular relation? And a derectangularizing sequence is just a particular way of defining a non-rectangular relation. So if we have a derectangularizing sequence, that corresponds quite directly to number p completeness of the corresponding CSP instance. And because because these two things are polynomial time equivalent, that gives you number p completeness of the matrix partitions problem. Okay, yeah. Now then the question is, okay, I've told you roughly how things work when the lists that we're allowed are purifying, but of course restricting to only being allowed particular lists was just a tool that we used to make the proof go through. So in particular, we want this to work if you're allowed the set of all possible lists. And the only way that the set of all possible lists can be purifying, well, that just says that every submatrix of your matrix is pure. Well, that just says the matrix is pure. So we've only solved the general problem for homomorphism problems, which didn't need to be solved because we already knew the answer. Okay, so what do we do if the lists that we've been given allow us access to non-pure submatrices of our matrix? What we do is we purify. So we take our impure lists and we contract them down to get lists which in fact are purifying, and then combine the answers that we get from these. So what do? We're given a graph G and an assignment of lists to each of the vertices. What we do is we compute several list functions, lambda 1 up to lambda t, and they have the following property. So first of all, each of these lambdas is purifying. Okay, so we originally had a single instance with a single list function. What we'll now do is give multiple list functions. And for each vertex and each one of these new list functions, we've only ever made the how do I want to say this? For every vertex, each of the lists assigned by these functions is a subset of the lists assigned by the original function. And the goal of all of this is that every matrix partition of the original graph, well, of the graph, we're not going to change the graph, that respects the original lists, respects exactly one of the new lists. Okay? So, if you like, we've partitioned the partitions into a bunch of purifying instances, where now, if we just add up the number of partitions for each of those instances, we get the answer that we were looking for. Okay, and it turns out that this purification algorithm does run in polynomial time, as long as there's no derectangularizing sequence, and in fact, as long as there's no length 2 derectangularizing sequence available. In this case, we're not even worried about the possibility of longer ones. Okay, so by transforming everything into pure instances, we can then use the CSP techniques from before to solve them, and we get our dichotomy that if you have one of these derectangularizing sequences available to you, then counting the partitions is not going to be complete. Otherwise, we have a polynomial time algorithm going via CSPs. And actually, I haven't mentioned it yet, but we use arc consistency to solve those CSP instances. I am pretty much at the end, so I think I'll stop there.
You may be expecting this question. Would it be possible to generalize this to an asymmetric case?
Yeah, it certainly makes sense to do that. What makes me think that there might not be any... and I was thinking of doing it myself. What makes me think it might not actually be so interesting is that this condition about derectangularizing sequences, it just doesn't care whether or not the graph is directed, because you're looking at arbitrary submatrices, not even principal submatrices. So kind of the subproblems are already slightly undirected. So it's not obvious that anything would happen. Or at least, it's not obvious that you'd get a different criterion. Yeah?
Would you expect the answer for listless version to be the same?
Depends what day of the week you ask me on. I'm honestly not sure. So for up to 4x4, it is the same. But it's hard to say whether it would be or not. I think between those of us who are looking at it, we conjectured it, yeah. But now I'm not sure that I believe the conjecture is true. But I can't give you any good reason for that.
Just some terminology. Albert Meyer used to say in his papers, conjecture when he thought it was true, and strong conjecture when he knew it was true. Right up for proof.
I think it's fair to say that we thought it was true when we wrote it and called it a conjecture.
Okay. So it's a strong conjecture.
It was not a strong conjecture.
Yeah, it was not a strong conjecture. Now I think it might be a question where the answer is maybe yes, rather than a conjecture. I'm not sure.
It's really conjecture. Good.
If not true, what do you think they might look like?
Yeah, you see, then someone says that, and it seems that, obviously the conjecture's true. Yeah, I have no idea.